Now some guy back when they developed pumps, they developed these things. And you know, another thing we do is we always rate the pressure in feet of head. What do you mean feet? We do things in PSI. Yeah, but you know, back when they first started doing pumps, all they were trying to do is move water from a stream up into a building or something like that. So all they had to do was overcome elevation. And how do we measure vertical elevation? We measure it in feet. We don't know anything about PSI, moving water from here to here. That isn't PSI, that's so many feet up. So, and originally all pump information was done in feet of head pressure. Okay, yeah, we had to move it 50 feet uphill. That was 50 feet ahead. Okay? Pretty simple. Now we got another little problem on this deal. We got to know what exit pressure we wanted out here. So we got to know that, and we pick that. If we want to have a big gun run 100 psi, we say, okay, that pressure is going to be 100 psi. Oh, now we got psi and we got feet ahead. We can convert between the two. There's, for every 1 psi equals 2.31 feet. So every time I go up 2.31 feet, it costs me another pound of pressure on the pump, another psi. If I go up 23.1 feet, it costs me 10 psi. It's just like saying, okay, we got so many feet or so many inches. I can go 1 foot or I can go 12 inches. Same idea, see? So that is called the exit pressure. That's what I like. They call it pressure head. Pressure head, the term often used is exit pressure. Now we got another little problem. We got to push that water up through this pipe. And so it costs us what? Friction. So we have friction head just driving it up the pipe. It's rubbing against the walls of the pipe, and it's costing us energy to get it from point A to point B. And we have to look at all the friction through all the bends, all the fittings, and we have valves in there, and all of that stuff, as well as just the lengths of pipe. And we can calculate that. We know from experience of all kinds of testing what the losses are going to be at a given flow in a given type of pipe for a given diameter, how much friction loss there will be. And last but not least, to get us through this beautiful design, is we have to have a certain amount of energy pushing on that water to get it into the suction pipe itself, get it moving. We have to start the water moving, and that is the velocity head. That's getting the water from just sitting here in the pond to start moving up the pipe. It takes a certain amount of inertia to do that, and we call that the velocity head. It's calculable. The velocity head, we call it h to v, it equals the velocity squared divided by 2 times the gravitational pull. The energy it takes to get it moving up into the pipe. Now g is, velocity is however fast it's going up the pipe. 2, 3, 4, 5 feet per second. And g always equals the gravitational constant. You knew we'd get into a little math before we were done here, didn't you? This is the math part of this whole operation. Now you add all of that stuff up and you get the total dynamic head. The TDH is the sum of the static suction lift plus the static discharge head. And I put lift here. The textbook, and correctly probably so, should say the words static suction head plus the discharge head equals the total elevation head. The exit pressure is added to that, the friction head is added to that, and the velocity head is added to that, and we get that big thing called TDH. Total dynamic head. Seth?
Does it make like a difference on the velocity head if it's like not in a pond but in a stream with some kind of flowing water?
No, the only thing that you're doing with the velocity head, the question was, would it matter what the water supply was, if it's a stream or a pond or a well or whatever? Not at all. What you're doing is simply getting the water to start moving up your pipe. Because it wouldn't matter what the supply was as long as it's just the pipe just sitting in the water, it's not moving in the pipe itself. So it's the energy it takes to get it into motion. It's the kinetic energy of the system. After calculating the total dynamic head on the pump, we have some information to be able to calculate the brake horsepower.